Welcome to G Fun Facts Online. Today we are diving deep into a topic that sits at the very intersection of automotive engineering, renewable energy, and global economics. The global transition to electric vehicles has been hailed as the silver bullet for decarbonizing transportation. Right now, as millions of EVs silently glide across the world's highways, they are actively driving down greenhouse gas emissions and drastically reducing our reliance on fossil fuels. But beneath the floorboards of these sleek modern vehicles lies a looming logistical challenge, which is also an unprecedented opportunity. What happens to the millions of lithium-ion batteries when they can no longer meet the rigorous demands of highway driving? For years, skeptics pointed to battery disposal as the Achilles heel of the electric revolution. They warned of a looming tsunami of hazardous electronic waste, arguing that the environmental cost of discarding millions of massive battery packs would outweigh the benefits of driving electric. However, as we look at the landscape today, that narrative has fundamentally shifted. Rather than becoming a toxic liability, retired EV batteries are emerging as the backbone of an entirely new, circular energy economy. Welcome to the era of the second life battery, a paradigm-shifting concept that is bridging the gap between clean transportation and a resilient, renewable energy grid. As we navigate through 2026, the second life EV battery market has evolved from a niche academic concept into a booming multi-billion-dollar industry. With massive implications for grid stability, renewable energy storage, rural electrification, and global supply chain resilience, repurposing automotive power is no longer just a good idea. It is an absolute economic and environmental imperative. To truly understand the sheer scale of the second life battery opportunity, we must first dismantle a persistent and widely held myth. That is the belief that EV batteries degrade as quickly as mobile phone batteries. For years, consumer anxiety surrounding electric vehicles was fueled by the fear that after 5 to 8 years, a vehicle's battery pack would be rendered completely useless, effectively turning a highly expensive car into an unsellable paperweight. This is fundamentally untrue. An electric vehicle battery is a complex, heavily engineered thermal system that is vastly superior to the basic power cells found in consumer electronics. Modern EV battery packs are managed by highly sophisticated battery management systems, or BMS, and advanced liquid cooling and heating infrastructure. These systems meticulously regulate the charging and discharging rates. They ensure the battery cells operate within an optimal temperature window, regardless of whether you are driving through a freezing winter or a scorching summer, thereby preventing catastrophic degradation. Recent comprehensive studies, including massive data analyses by the P3 Group and AVILOO, which analyzed over 7,000 vehicles in real-world conditions, have definitively proven the incredible resilience of EV batteries. The data reveals a fascinating truth. The vast majority of EV batteries retain more than 80% of their original capacity, even after traversing 200,000 kilometers, which is roughly 124,000 miles. While an initial capacity drop is usually observed in the first 30,000 kilometers, the degradation curve quickly flattens out, resulting in a slow, highly predictable linear decline over the following decade. Let us break down why this degradation happens in the first place. Battery degradation is primarily driven by two factors. The first is cyclical aging. This is the wear and tear resulting from repeated charging and discharging cycles. Extreme behaviors, such as exclusively relying on direct current fast chargers or routinely draining the battery all the way down to 0%, can accelerate this process. The second factor is calendar aging. These are the natural chemical changes that occur over time, regardless of whether the vehicle is driven every day or parked in a garage for a month. Over time, there is a buildup of what is called the solid electrolyte interphase layer and the plating of lithium onto the anode. These highly complex chemical reactions slowly trap active lithium ions, marginally reducing the pack's overall energy capacity. By the time a battery degrades to roughly 70 to 80% of its original capacity, it typically reaches the end of its first life in an automotive application. At this stage, the battery may no longer deliver the rapid acceleration or the reliable 300-mile range demanded by modern drivers. However, it still holds a massive reservoir of energy. Think about it this way. A 100 kilowatt-hour battery pack retired at 80% health still possesses 80 kilowatt-hours of storage capacity. That is more than enough to power an average residential home for several days. Throwing this battery into a massive industrial shredder for raw material recycling at this stage would be a tragic waste of highly functional, expensive engineering. This brings us to the concept of the circular battery economy. As millions of first-generation EVs reach their 10 to 15-year lifespans, the industry is adopting a model that prioritizes extracting the maximum possible utility from every manufactured battery cell before it is finally broken down into its base elements. The life cycle stages of an EV battery can now be categorized into 3 distinct phases. First is the first life, the automotive phase. The battery serves its primary purpose, powering an electric vehicle for 10 to 15 years, or up to 200,000 plus miles. Second is the second life, the stationary storage phase. Once removed from the vehicle, the battery is tested, graded, and repurposed. Because stationary applications do not require rapid, heavy bursts of power, nor do they have strict weight and aerodynamic space constraints, the retired battery can easily serve for an additional 10 to 15 years, storing energy for the grid, businesses, or homes. Finally, the third phase is end of life, the recycling phase. Only after the battery has exhausted its secondary utility, typically dropping below 50% total capacity, is it sent to a recycling facility. Here, complex hydrometallurgical or pyrometallurgical processes recover up to 95% of critical minerals like lithium, cobalt, nickel, and copper. These precious elements are then injected right back into the manufacturing pipeline to create brand new batteries. By inserting a second life between the vehicle and the recycling plant, we effectively double the useful lifespan of the battery pack. This delay is incredibly valuable. It drastically reduces the immediate demand for new, virgin mineral mining, cuts down the carbon footprint associated with manufacturing entirely new energy storage systems, and significantly lowers the cost of grid-scale energy storage. But how exactly do we transition a battery from a car chassis to a stationary storage rack? It is not as simple as plug and play. EV batteries are intricately integrated into the structural architecture of the vehicles. Safely repurposing them requires a brilliant blend of advanced hardware engineering, software analytics, and strict safety protocols. The first step is disassembly and inspection. When an EV reaches the end of its roadworthy life, highly trained technicians safely remove the high-voltage battery pack. The pack undergoes a rigorous visual and physical inspection to ensure the casing has not been compromised by traffic accidents, water intrusion, or extreme thermal events. Depending on the repurposing strategy, the pack may be kept fully intact, disassembled into smaller modules, or broken all the way down to individual power cells. Keeping the pack intact is the most cost-effective method, but disassembling into modules allows engineers to weed out the few bad apple cells that may be dragging down the performance of the entire unit. However, the rise of cell-to-pack and cell-to-chassis designs in newer electric vehicles presents a unique engineering hurdle. These modern designs utilize incredibly strong structural adhesives and complex spot welding to maximize energy density and vehicle rigidity. While this is excellent for the performance of the car, these adhesives make non-destructive disassembly highly challenging, often requiring specialized solvents or thermal treatments to separate modules for second life use. The next and perhaps most critical step is state of health estimation and AI diagnostics. The state of health is a metric representing the battery's remaining capacity and internal resistance. Because no two drivers treat their vehicles exactly the same way, two identical EV batteries retired on the exact same day can have vastly different state of health profiles. Engineers utilize techniques like incremental capacity analysis to track the internal electrochemical variations, plotting voltage against charge to detect the loss of active lithium inventory, or the degradation of the anode. In 2026, artificial intelligence and machine learning have absolutely revolutionized this grading process. Companies utilizing AI-driven software can rapidly analyze historical charge cycles, thermal data, and real-time impedance to predict the battery's remaining useful life with stunning accuracy. AI ensures that only batteries with matching degradation profiles are paired together in a new storage array. This prevents a weaker module from bottlenecking the performance of a stronger one. Startups like Rejoule have commercialized proprietary hardware and software solutions that slash the time it takes to assess battery health, clearing a massive bottleneck in the repurposing supply chain. Once graded, the modules undergo reintegration. They are reconfigured into stationary storage racks. Because they have been separated from the EV's proprietary onboard computer system, they require a completely new, custom battery management system. This new BMS acts as the brain of the storage unit, monitoring voltage, balancing the cells, managing thermal conditions, and communicating with the external power inverter to ensure smooth, safe integration with the electrical grid. Now, where are all these repurposed batteries going? The applications for Second Life EV batteries are as diverse as the energy sector itself. By offering a lower-cost alternative to newly manufactured First Life lithium-ion systems, repurposed batteries are unlocking energy storage opportunities across the globe. Let us look at grid-scale storage and renewable integration. The global transition to renewable energy sources like solar and wind faces a fundamental challenge: intermittency. The sun does not always shine, and the wind does not always blow. To maintain grid stability, utility companies require massive energy storage systems to capture excess power generated during peak production hours and dispatch it during peak demand. Second Life EV batteries are perfectly suited for this role. Arrayed in megawatt-scale shipping containers, these repurposed packs perform critical grid services. They provide what is known as peak shaving. This means absorbing cheap, abundant solar energy at noon and discharging it at 6 in the evening when people return home and turn on their appliances. This simple act saves utility companies from firing up expensive, highly polluting natural gas peaker plants. Real-world examples are already operating beautifully. Facilities like the Johan Cruyff Arena in Amsterdam use a 3 megawatt-hour storage system built entirely from repurposed EV batteries to pair with the stadium's rooftop solar panels, ensuring uninterrupted power during major sporting events. Another massive application is commercial and industrial backup. For manufacturing plants, massive data centers, and telecommunications towers, a power outage can result in millions of dollars in lost revenue. Traditionally, these facilities relied on noisy, polluting diesel generators or heavy, inefficient lead-acid batteries for backup power. Second Life lithium-ion batteries provide a clean, silent, and highly responsive alternative. Furthermore, businesses can use these batteries to perform energy arbitrage. They buy electricity from the grid in the middle of the night when rates are incredibly low, store it in the repurposed EV batteries, and run their facilities entirely off the batteries during the day when utility rates spike. Ironically, Second Life batteries are also playing a crucial role in expanding the very EV revolution that created them by supporting EV charging infrastructure. As the adoption of direct current fast chargers accelerates, the sudden, massive draw of electricity required to charge multiple vehicles simultaneously can heavily strain local power grids. This often triggers exorbitant demand charges from utility companies. By installing Second Life battery buffers at charging stations, operators can trickle charge the stationary batteries from the grid at low speeds throughout the day, and then dump that stored energy rapidly into visiting EVs. This circumvents the need for expensive grid upgrades, lowers operating costs, and ensures fast charging is viable, even in remote areas with older, weaker electrical infrastructure. We are also seeing a boom in residential home storage. With the surging popularity of residential rooftop solar panels, homeowners are increasingly looking for ways to store their generated electricity for nighttime use. While brand new home battery systems can be prohibitively expensive, systems built from Second Life EV modules can reduce hardware costs significantly. Studies have shown that utilizing Second Life batteries for home storage can cut a homeowner's electricity bill by 42 to 64% compared to relying solely on the local power grid. But perhaps the most profound impact of Second Life batteries is felt in the global south and through rural electrification. In remote, off-grid regions where energy poverty is a daily reality, pairing repurposed EV batteries with solar microgrids provides a stable, low-cost path to electrification. A breakthrough study published in Scientific Reports highlighted how Second Life EV batteries proved to be a highly viable and cost-effective solution for electrifying rural primary schools in Kenya. Startups like Canada's Moment Energy are actively transforming EV batteries into microgrid solutions that provide clean, reliable power to off-grid communities, replacing expensive and polluting diesel generators with silent, sustainable energy. From an economic standpoint, the market dynamics are staggering. As of 2026, the global Second Life EV battery market has entered a period of explosive, exponential growth. Valued at approximately $1.6 to $1.7 billion in 2025 and 2026, The market is aggressively tracking toward an estimated $32 billion to $59 billion by the mid-2030s. It boasts a staggering compound annual growth rate of over 25 to 40%. The volume projections are equally mind-blowing. Industry analysts estimate that the global availability of second-life batteries will skyrocket from roughly 25 to 30 gigawatt-hours in 2025 to an astounding 330 to 350 gigawatt-hours by 2030. To put that monumental number into perspective, 350 gigawatt-hours is enough stored energy to power tens of millions of homes. When we look at regional leadership, the Asia-Pacific region, led primarily by China, dominates the global second-life battery market. China was the earliest and most aggressive adopter of electric mobility. Consequently, they are experiencing the first massive wave of retiring batteries. With robust government policies, heavy investments in renewable energy, and established battery manufacturing ecosystems, the APAC region is the undisputed volume leader. Meanwhile, Europe is widely considered the fastest-growing market and the undeniable global leader in regulatory innovation. Driven by stringent carbon neutrality goals, rapid EV adoption, and high energy costs, European companies are aggressively deploying second-life battery energy storage systems. The region's deep commitment to a circular economy has fostered a highly collaborative environment between automotive manufacturers and clean energy startups. In North America, the United States and Canada are rapidly scaling their second-life infrastructure, bolstered by massive federal incentives. Companies like B2U Storage Solutions have already deployed massive, commercial-scale solar-plus storage facilities, utilizing hundreds of intact used EV batteries in places like California, mathematically proving the commercial viability of large-scale repurposing. A market expanding this rapidly naturally requires robust regulatory guardrails. Historically, the management of end-of-life vehicle batteries was a legal gray area. Unlike internal combustion engine lead-acid batteries, which have long-established recycling protocols, lithium-ion EV batteries operated in a Wild West regulatory vacuum. However, the 2026 regulatory landscape has radically transformed, with policymakers moving aggressively to standardize and incentivize the second-life ecosystem. The European Union has set the undisputed gold standard for battery regulation. The sweeping EU battery regulation, rolled out in phases through 2025 and beyond, mandates strict adherence to circular economy principles. Under the Extended Producer Responsibility mandate, automakers and battery producers are legally responsible for the end-of-life management of their products. They cannot simply wash their hands of the battery once the car is sold to the consumer. They must legally finance and facilitate its collection, repurposing, or recycling. Crucially, in late 2025, the EU introduced EN 18061-2025, a landmark standard explicitly focused on the safe repurposing of EV batteries for energy storage. This framework standardizes the safety rules, testing protocols, and vital documentation required for second-life applications, effectively transforming an ad hoc practice into a certified, highly regulated global industry. Furthermore, by 2027, the EU requires the implementation of a digital battery passport. This is a massive leap forward. Every industrial and EV battery over 2 kilowatt-hours will feature a digital twin, a transparent, immutable digital record detailing the battery's manufacturing origin, chemical composition, overall carbon footprint, operational history, and real-time state of health. This digital passport is an absolute game-changer for the second-life market. By completely eliminating information asymmetry, repurposers no longer have to guess a battery's driving history. They can instantly verify its exact suitability for a second life, drastically reducing assessment costs and liability risks. The EU's aggressive stance is causing massive ripple effects across the globe. While the United States currently lacks a unified federal battery recycling or repurposing mandate, state-level actions and massive federal funding initiatives are stepping in to fill the void. The U.S. government has poured billions into domestic battery manufacturing and recycling through recent legislation, indirectly stimulating the second-life market by funding vital research into battery diagnostics and circular supply chains. Industry advocates continue to push for policies that mandate automakers to transparently share critical battery data with third-party repurposers, ensuring an open, safe, and competitive aftermarket. Simultaneously, governments worldwide are establishing mandates for recycled material content. By 2031, The EU requires new batteries to contain a minimum percentage of recycled cobalt, lead, lithium, and nickel. While this obviously drives the recycling industry, second life applications serve as the critical intermediary step. They extract decades of additional utility from the battery before it is ultimately melted down to satisfy these strict recycled content quotas. This represents a rare alignment of robust economic opportunity and profound environmental stewardship. From an environmental perspective, second life batteries represent a massive reduction in greenhouse gas emissions. Manufacturing a new lithium-ion battery is an incredibly energy-intensive process, heavily reliant on the extraction of virgin minerals. Mining these critical raw materials often entails significant environmental degradation, massive water consumption, and complex geopolitical supply chain vulnerabilities. By substituting newly manufactured grid storage batteries with repurposed EV batteries, we instantly offset the carbon emissions and mining impact associated with new battery production. The life cycle emissions of the battery are amortized over 20 to 25 years instead of just 10, drastically lowering the overall ecological footprint of the clean energy transition. From an economic perspective, second life batteries are violently disrupting the energy storage market. Because the massive capital cost of the battery was largely subsidized during its first life in the electric vehicle, repurposed batteries can be acquired and deployed at a fraction of the cost of entirely new systems. This incredible cost advantage lowers the financial barrier to entry for renewable energy projects, making solar plus storage economically viable for smaller businesses, residential communities, and developing nations that previously could not afford the clean energy transition. However, despite the incredible undeniable momentum, the second life battery market is not without its major hurdles. The biggest engineering headache currently facing the industry is the lack of standardization across automakers. A Tesla battery pack is fundamentally different in internal chemistry, physical shape, electrical voltage, and cooling architecture from a Nissan, Ford, or Hyundai pack. Repurposers must design highly flexible hardware and software systems capable of integrating radically different batteries, or they must focus on massive volumes of a single vehicle model to achieve basic economies of scale. Another major challenge is shifting chemistries. The automotive industry is rapidly pivoting away from nickel-manganese-cobalt chemistries toward lithium iron phosphate, or LFP chemistries. While LFP batteries are cheaper, much safer, and last longer, they have a notoriously flatter voltage discharge curve. This flat curve makes it significantly more difficult for diagnostic software to accurately estimate their true state of health. The second life industry must continuously adapt its complex diagnostic algorithms to handle these evolving, tricky cell chemistries. Additionally, we must consider the rapidly declining costs of new batteries. As global gigafactories scale up their massive production lines, the cost of brand new LFP batteries continues to plummet year after year. If the price of new batteries drops low enough, the economic margin for second life batteries could be severely squeezed. To survive this potential price war, repurposers must ruthlessly optimize their logistics, deploy fully automated testing, and streamline their reassembly processes to ensure repurposed packs remain the absolute most cost-effective solution on the global market. Finally, there is the issue of transport and logistics. Moving massive, heavy, high-voltage battery packs that are legally classified as hazardous materials is incredibly expensive and heavily regulated by transport authorities. Establishing localized, regional hubs for testing and repurposing is absolutely essential to keep logistical costs low and transportation emissions in check. But ultimately, the story of the second life EV battery is a testament to human ingenuity and the fundamental principles of the circular economy. It transforms a perceived massive liability, millions of aging electric vehicles, into one of the most vital technological assets of the 21st century. As we look ahead toward the 2030s, the rigid line between the automotive industry and the energy sector will continue to rapidly blur. The electric car parked in your driveway is no longer just a simple mode of transportation. It is an active, vital node in the global energy grid, and its powerful battery will live on to light up stadiums, secure massive data centers, and bring reliable electricity to off-grid villages long after the car's tires have stopped spinning. By extending the lifespan of these remarkable energy reservoirs, we are honoring the materials painstakingly extracted from the earth, aggressively driving down the cost of renewable energy, and taking a massive, definitive step toward a truly sustainable future. The second life of the EV battery proves that in the modern energy transition, Absolutely nothing is wasted, and everything has the potential for a powerful, world-changing reinvention. Thank you for exploring this fascinating topic with us today, right here on G Fun Facts Online.